Today, it takes little time to snap together an autonomous digital workflow. You write a prompt, connect tools, and watch the pieces lock into place. Building a working AI agent that can complete a meaningful task from start to finish is easier than ever. We can create impressive, demoable agents in an afternoon. When that initial prototype succeeds, the natural instinct is to push it further. If a system handles a narrow task perfectly, the logical next step is to give it more tasks, add many more steps, and less human supervision. But transitioning from a prototype to an enterprise system reveals a structural problem. Scaling agents changes the underlying physics of how the system behaves. This schematic compares two scaling models. On the left is traditional software engineering. As user demand grows, you duplicate identical server nodes to process the influx of requests. This is a solved problem. You manage higher throughput by adding infrastructure, more CPU, more memory, or duplicating those nodes horizontally. The system produces the exact same behavior, just at a higher volume. Now look at the right pathway, representing an agentic system. Scaling here rarely means handling more users. Instead, distinct functional tool blocks and domain context libraries are injected straight into the single agent node. We are asking the system to do more. We are expanding its scope to handle broader, more complex tasks with less supervision, cramming entirely new capabilities inside that single functional boundary. This line graph demonstrates how this shift alters the mathematics of the entire system. As the scope expands, the latency and processing time required for a single task spikes dramatically. Development teams frequently mix these two definitions, approaching capability expansion with the tools of throughput management. Throwing more compute at the problem, or expanding the model's context window, does not resolve the friction introduced by a massive, unwieldy task load. Forcing a lone agent to manage a continuously widening scope guarantees a drop in reliability. Building reliable agents at scale is a systems design problem, regardless of the underlying model's size. To increase autonomous intelligence without triggering a collapse, we have to rethink how we structure decision-making and step away from the monolithic design. This diagram illustrates an autonomous agent's continuous cycle: plan, execute, memory, and reflect. It breaks a prompt into a plan, triggers a tool API, writes to memory, and evaluates success. For tightly bounded problems, this is highly efficient with invisible latency and minimal token usage. Because the variables are strictly limited, the system executes a handful of precise decisions, achieves the designated goal, and stops entirely. This initial success creates a false sense of security. It convinces developers that they can simply bolt new features onto the existing loop without changing the underlying architecture. Requesting broader responsibilities means attaching dozens of new tool nodes directly to the execution phase. The physical cost changes immediately. The model is forced to spend heavy compute scanning through 50 new options to determine the correct path. Evaluating larger toolsets increases decision time proportionally. Expanded responsibilities also generate excess data. The memory database swells, filling with chaotic data points from new, unrelated domains. This bloated memory state means the agent must carry a massive load of irrelevant context forward into every subsequent step of the cycle. To locate the actual signal, the model burns heavy computation filtering noise. This dilution cascades into the reflection phase. Overwhelmed by bloated context, the agent loses its ability to accurately judge its own actions. Checking work becomes extensive, and reflection structurally unreliable. This graph overlay demonstrates that token usage, latency, and operational costs do not scale linearly. They curve sharply upward with every added decision. Adding 50 features to a single agent multiplies the complexity of every internal calculation, rather than simply adding 50 steps. An interaction that initially took 2 seconds and cost fractions of a cent transforms into a fragile process that is incredibly slow and highly expensive. By centralizing all responsibility in one place, the monolithic agent becomes a bottleneck, driving up the financial cost of every successful outcome to an unsustainable level. Beyond latency and cost, forcing a single agent to manage high uncertainty exposes the system to a distinct structural threat: error propagation. Consider an autonomous travel agent. We submit a prompt to plan a Washington itinerary. The agent calculates probabilities and misinterprets the request as Washington, D.C., writing this microscopic error directly into its continuous memory state. Running autonomously without human intervention, there's no checkpoint to flag the mistake. The corrupted assumption acts as absolute truth, feeding incorrect parameters into flight search, hotel bookings, and transit logistics. The agent successfully completes every subtask requested, entirely unaware that the final output is useless to the user. Failures in an autonomous architecture propagate and compound across time, turning a single oversight into a structural collapse of the entire workflow. To prevent collapse, we have to stop trying to scale the individual agent. The solution is to decompose the system itself. We implement what is known as bounded decision-making. We take the single monolithic node and distributes its capabilities across a network of microagents. Each component in this network operates with strict boundaries. It carries a fraction of the context, uses limited tools, and makes drastically fewer decisions. If one node makes a mistake, the error is trapped within that specific boundary rather than compounding through a shared continuous memory loop. This multi-agent architecture introduces an engineering challenge, deciding where to place new capabilities. One option is horizontal scaling, introducing a new dedicated agent like a localized fact-checker. This separates reusable logic but increases communication latency. The alternative is vertical scaling, embedding tightly coupled subfunctions inside an existing agent, for instance, giving a retrieval agent a built-in data filter. Vertical placement eliminates coordination latency because the steps share the exact same context. However, it risks reintroducing monolithic complexity within that specific node. Navigating this trade-off requires a strict rule for capability placement. If a capability is independent and reusable across multiple tasks, you split it horizontally. If it relies heavily on shared sequential context, you embed it vertically. Achieving scale is entirely dependent on deliberately choosing where your system's complexity is allowed to accumulate. This is the end state of a successfully scaled architecture. We see a dynamic network where multiple bounded nodes exchange localized data efficiently. A central coordinator agent manages the intake, evaluating user prompts and delegating discrete steps to the specialized subagents. Execution speeds remain high, and individual token costs stay exceptionally low, because no single node is ever burdened with analyzing the entire scope of the operation. An error generated by a retrieval agent is immediately caught and corrected by a parallel evaluator agent before the mistake can poison the system's broader memory state. By changing the distribution of responsibility, the architecture is equipped to survive its own complexity. The ultimate constraint of autonomous AI is that scaling amplifies every characteristic of a system. It multiplies the capabilities, but it also multiplies every inherent flaw, cost, and latency. Trying to power through these physical constraints by deploying larger foundation models is a dead end for production-level reliability. The path forward lies entirely in systems design. We must build networks of orchestrated microagents that enforce strict boundaries around their cognitive tasks. High-performing teams treat enterprise AI as a distributed ecosystem of intelligent microservices. The organizations that deploy the most effective AI won't necessarily possess the highest parameter foundation model. They will be the ones with the structural architecture that allows intelligence to compound safely at scale.